In this lesson, we are going to explore the properties of atoms on the periodic table, and we're going to see some very interesting patterns. We're going to take a look at, in this section, we're going to take a look at electronegativity and ionization energy. And then we're going to see how that relates to something called metallic character and non-metallic character. So let's start with electronegativity and a definition. Well, first of all, an abbreviation. Electronegativity, you're going to see that I will abbreviate it as EN. A definition of electronegativity, it is the nucleus, it's the measure, well, it's the nucleus's, that's a little tricky to say, the nucleus's attraction for electrons the atom is sharing with another atom. So the key thing I want you to take away here, it is electronegativity is a measure of how well a nucleus can attract electrons to itself. Excuse me. What we are going to do to see what this trend actually looks like, we're going to refer to table S. Right? Remember, table S has all this information. And what we're going to be looking is the electronegativity values. Now, electronegativity values are more of a scale. Notice that there's numbers that go from essentially down to 0, but the highest electronegativity that an element can have is a 4.0. So electronegativity is there's no unit here. It's a ranking. Basically, it's comparing elements to other elements and how well, when you're comparing those elements, how well an atom can attract the shared electrons. Okay? So no units here on electronegativity. It's just a scale of 0 to 4. When we start looking up electronegativity values, we're going to look up the values for period 3, this row right here, and we're going to look up the values for group 2, just as our representative group and period, to look for a trend. So if we look up those numbers for each element, we're going to see a 0.9, a 1.3, 1.6, 1.9, 2.2, 2.6, 3.2, and then you'll notice something actually very interesting. You'll notice that the noble gases do not have electronegative values. And the reason for that, remember, electronegativity is an attraction for electrons that the atom is sharing with another atom. But noble gases, since they already have 8 valence electrons, noble gases don't bond with other elements. So therefore, we have no way there's nothing to measure. So we're just going to put a dash through here, and every noble gas would have no electronegativity. And I just realized all these numbers should be down here. Okay, so as we go across left to right, we see that the electronegativity values increase. Okay. Well, actually, let's finish the group 2. So group 2, we look up the electronegativity values. We have 1.6 down to 1.3, 1.0, 1.0, 0.9, and 0.9. All right, so what we see here is that the electronegativity values here are decreasing. So let's talk about what's happening. Within a vertical group, the electronegativity values decrease, okay, as you go down that group. So the question is, why? Well, it all goes back to atomic radius. If you recall, going down a group, the atoms are getting larger because, if you recall, there's more principal energy levels being added, so those valence electrons are further away from the nucleus. So we're going to tie the reason for the decrease in electronegativity, we're going to tie that to atomic radius. So we're going to say as atomic radius gets bigger, going down that group, as the atomic radius gets bigger, the valence electrons are further from the nucleus. So as the atomic radius gets bigger, the valence electrons are further from the nucleus. When those valence electrons are further from the nucleus, the nucleus has a harder time attracting those electrons as they get further away. Okay, so we're going to say, therefore, it is harder for the nucleus to attract the shared electron. Right, and so it has the nucleus has a harder time holding on to those electrons as they get further away. So we say that their attraction is weaker, and so therefore the electronegativity is smaller. As we go across the period, right, and then you can see I mistakenly put those numbers in the wrong boxes, but as we go across, you can see that those numbers are getting bigger, so electronegativity values are increasing. Again, this is tied into the atomic radius. If you recall, as you go left to right within a period, the atomic radius is decreasing due to increased nuclear charge. So let's talk about this. As atomic radius gets smaller, as you go left to right within the nucleus, the valence electrons are closer to the nucleus. And it is therefore easier for the nucleus to attract those valence electrons, to attract the shared electrons. So it's really the same reasoning. It's really all about the size of the atom. The smaller the atom, the closer the shared electrons are to the nucleus, and therefore the nucleus has a greater hold on them. So we give it a higher ranking number. Okay. Let's go back and just note here that noble gases do not share electrons because they already have 8. So therefore, they do not have electronegativity values. All right, let's continue on and talk about ionization energy. Turning the page to the next page of notes. And ionization energy, let's talk about the abbreviation we're going to use for it. We're going to use IE as the abbreviation. Definition here, it is the energy required to remove the most loosely held valence electron. This is technically called the first ionization energy. First ionization energy is the energy required to remove the most loosely held valence electron. There is something called a second ionization energy, which is the energy required to remove the second most loosely held valence electron. And so theoretically, there's a third ionization energy, so on and so forth. But when we talk about ionization energy, we are almost always talking about the first ionization energy. All right, we're going to look up these values again from table S. We're going to look them up for period 3 here, and we're going to look them up for group 2, just to use those as representative periods and representative groups. When we come to reference table S, I am getting that information here from first ionization energy. The unit is kilojoules per mole. We haven't talked about the mole yet, but this is the kilojoules per a given specific number of atoms. Okay, so we are looking at these numbers here. We can see that some of them are pretty big numbers. But when we look them up and write them down in this periodic table, we have the number 900 here, 738, in this spot, 590, 549, 503, 509. Across period 3, we have 496, 738, we already wrote that in, 578, 787, 1012, 1000, 1251, and then 1521. So there is a little blip in the trend as we go left to right. If you go left to right, you can see that generally the ionization energy is increasing. There's a little blip, but overall we're focusing on the big trend. The ionization energy increases. Okay, so we're going to say that here. The ionization energy increases within a horizontal period left to right. As we go top down, 900 down, we can see that the ionization energy is decreasing. Okay, so let's talk about this. Again, this is going to be tied into the size of the atom, right? As the atom gets bigger, it takes less energy to remove that most loosely held electron. That is simply because that most loosely held electron is now getting further and further and further and further away from the nucleus. The nucleus cannot hold on to it as strongly, and so it takes less energy. So let's talk about this. As the atoms get bigger, as you go down the group, the atoms get bigger. The valence electron are further from the nucleus. What this means, it takes less energy is needed to remove the electron. Right? It basically gets easier to remove the valence electron. Same rationale as we go left to right within a horizontal period. We see that it's taking more energy to remove that valence electron, right? It's taking more energy to remove that electron. And it's all, again, once again, it is tied to the size of the atoms, right? As you go left to right, atoms are getting smaller because of the increased nuclear charge. So as the atoms get smaller, valence electrons are closer to the nucleus. That means that more energy is needed to remove the electron. It effectively gets harder to remove the electron. All right, we're going to finish up this video talking about metallic character and what that means and how ionization energy and electronegativity are tied into this. Okay. All right, so metallic character is basically, it is the level of reactivity of a metal. Right, it's a level of reactivity of a metal, basically how easily it will lose an electron. Okay, and if we think about that, if metals are going to react by losing an electron, we have something that can tell us how easy it will be to lose an electron. So metallic character is based on ionization energy. So if an element, if it has a low ionization energy and really a low electronegativity, okay, those are definitely tied in together. With if the lower the ionization energy, the lower the electronegativity, then that means the greater the metallic character. So the lower the ionization energy, and the electronegativity, the greater the metallic character. Generally, what you are going to find is if we take a look at the periodic table, I'm going to pull it open here for you to see. You're going to find that the elements with the lowest ionization energy and electronegativity are going to be, as you go down the group, elements become more metallic, and as you go closer to the left side of the periodic table, elements become more metallic. So if you had to compare two elements, generally speaking, scandium to cesium, for example, right? Cesium would have a greater metallic character than scandium. And we could confirm that most likely by looking up the ionization energies and electronegativities on table S. Okay, but you can also find it, the lower left side of the periodic table are the most metallic. Okay, the lower left side of the periodic table. So let's talk about nonmetallic character. This is the level of reactivity of a nonmetal. And nonmetals do kind of the opposite of what metals do, where metals will lose an electron. Nonmetals tend to gain electrons. So we're looking at how easily the nonmetal will gain an electron, right? And so we have a measure of that. Electronegativity, if you recall, is the measure of the attraction of a pair of shared electrons. So if we are looking for elements with high ionization energy or high electronegativity, then typically that element will have a high non-metallic character. Or you can think of it the other way around. The more non-metallic it is, the less metallic it becomes. So what we are now looking for is if there is a high ionization energy or a high electronegativity, then we say that that substance has a high non-metallic character. Or you could also say a low metallic character, because they are definitely opposite of one another. The more metallic it is, the less non-metallic it is. The more non-metallic it is, the less metallic it becomes. So where can we find the most non-metallic character element? Well, if you go to the periodic table, remember the nonmetals are here. Okay. The most non-metallic elements are going to be in this upper right corner. Okay, so the most non-metallic are the upper right of the periodic table. All right, this is where we are going to stop this video lesson for now. We will pick up with the next section in the next unit or in the next video, and I will see you back in the classroom.